So the next extension that we're going to look at with the harmonic series is how many terms would it take to get a particular number? We discussed the fact that when you add up the number of terms, each grouping is like a half. So if I wanted to know what must be added together to get a sum of 3, then how many of those half blocks would that be? You'll notice that there will be some maneuvering that does occur with the harmonic series, that it doesn't always start with 1. In particular, you'll notice our example that we're looking at here, it doesn't say 1 plus and then a half, a third, a fourth, a fifth, but rather starts at 1/2. And we will have to accommodate for that as we approach this. But let's think back to our lesson from the other day. When we looked at the harmonic series, we recognized the fact that it actually has a grouping of halves. And I'm just going to continue this for just a moment just so that we can see the next grouping, right? And we would have 1/9 plus 1/10 plus all the way up to 1/16. And then it would go again plus 1/17, and it would keep going. So I'm just going to leave it like that. But I want us to recognize some patterns that you should see here. If you look at the number of terms, since we're trying to figure out the number of terms here, we'll notice that there's one term here. If this said it wanted me to add together to get a half, I would only need one term. If it said it wanted the number 1, then it would require this one and these two together. Can you follow that? If we wanted the next one, it would involve these 4. And then we would have the 8, and then we would have the 16. Now, does anybody notice the relationship between the number of terms that we have here? We have 2, 4, 8. It's not 6. It's not that they're even, but rather that they are powers of 2. In fact, even this 1 is a power of 2. It would be the power of 2 to the 0, and this would be 2 to the 1, and 2 squared, 2 cubed, 2 to the 4th. So if we want the number of terms that this would take, it's amazing how that actually works, doesn't it? And if we were to throw this all together even more so, as a whole, if I want the total number of terms, we can see, okay, there are 3 here. And then if we were to add that to the 4, that would give me 4 more, so together would make 7, right? And then we could add this 8 that we have here, and that would make 15 total. And so what it looks like is that in and of itself is a power of 2, just subtracting 1. Well, where would that 1 have come from? Where's that 1 missing from? Well, if you think about it, it's missing this first term, that 1. The harmonic series is actually written, honestly, just coincidentally, I don't know if you would call it that, but mathematically you can see the beauty of the pattern of powers of 2 within the harmonic series. So what we're looking at here is we want to figure out how would we add together to get the sum of 3. Let's just start there, okay? And we're starting at 1/2. Let's just think through this. If I want to get the sum of 3, okay, so let's see here. We're going to write down the sum that we're going to need and then the number of terms. So let's just do it like in a chart, okay? So if I wanted the sum of 1, I would need this one and I would need that together. And that would give me the sum of a half, and then that half would together give me the sum of 1. Do you follow that? And I notice that there are 3 terms there, right? What I want to do, though, is write this in the form of a power of 2 eventually. So I'm going to write this down. So that's where we're headed with this, okay? So the number of terms we've got here is 3. If I want the sum of 2, let's try that. So I would have the sum of 1. I would have to have all 3 of those. And then I would have to have this group here, right? Oops, sorry. I went too far. So I would have to have that group, so that adds 4 more, so that would make 7. And I would need this half to give me another whole 1, right? So I have these 8 terms, the 4 terms here, so that's 12, plus the 3, that gives me 15. All right, let's say I want the sum of 3. Then I'm going to have to add the next group of 16 and the group of 32, because those two together are going to give me that next piece. Are you with me on that? But see, these numbers are going to get incredibly large. Is there a way that I can write this in the form of a power of 2? Obviously, we talked about the fact that there's a power of 2 pattern here. So do you all see that this would be the same as 2 squared minus 1? 4 minus 1. And then this would be 2 to the 4th minus 1. The next one, if you think about it, if we were to add that 48 to this, okay, that would be 63. How could I write that? That would be 2 to the 6th minus 1. Again, this minus 1, I want you to notice, is actually because that 1 is missing here on the front side of the harmonic series. That's why the minus 1. And the powers of 2 that you see here, it becomes, so if I wanted 4, I don't even need to count it up. Do you see that it also has a pattern, 2 to the 8th minus 1. So if I want 5, it would be 2 to the 10th minus 1. Isn't that beautiful? All the significance of that. And so we can actually look to see all the patterns that we have here. We're going to continue to look at this and how we can apply it in furthering each of these examples. But you can just see, if I wanted 7, we would just need to do 2 more groups each time, right? So for 6, it would be 2 to the 12th minus 1. If I wanted 7, it would be 2 to the 14th minus 1. And it's just a neat pattern. We'll do some more examples with that. The last thing I want to do in dealing with the harmonic series today is to look again at how we can show that even something that looks like this, how is that the harmonic series? We mentioned before that harmonic series, we can tell because of the addition that goes on. And when I look at this, even though it's not multiples of 3, I can see that what's happening here is I'm adding by 3 to get to each. So how does that also show that it's the harmonic series? Well, in essence, what you want to do, okay, is we want to find a multiple of 3. Why 3? Because we're adding by 3. Because we're adding by 3, we want to choose a multiple of 3. Now you might think, okay, well then let's do 1/3. The problem with using 1/3 is 1/3 is bigger than 1/7. So what we want to do is choose a multiple of 3 that is less than 7. Because the 7 is what's here in the bottom, so that I can compare. I know that this is greater than 1/9 plus 1/12 plus 1/15 plus 1/18. Let me explain that again. If I know that this 1/9 series is equal to infinity, and we also would know that this is bigger than the 1/9 series, right? Because 1/7 is bigger than 1/9. Think of a pizza, you'd want 1/7 versus dividing it by 9. Then that must mean that if 1/9 series is infinity, then this must also be infinity. So that's the direction of our proof. So here's what we're going to do. Again, we're going to choose a multiple of 3 that's less than 7. So once again, we're going to use the 1/9. Could we have used 1/12? Sure you could have. But 1/9 is closer. And then I'm going to say, all right, now let's factor out 1/9. When I factor out 1/9, I have 1 plus, and what do you see? Oh, sorry, we're going to factor out 1/3. I apologize. I didn't need to do that. Factor out 1/3. Apologize for that mistake. Why 1/3? Because it's multiples of 3. So when I do that, I have 1/3, 1/4, 1/5, 1/6. And again, this is the harmonic series. So I know it's equal to infinity. And therefore, if this is equal to infinity and it is smaller than the other side, then 1/7 plus 1/10 plus 1/13 plus blah, 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 blah has got to be also greater than infinity. Does that make sense? Once again, you'll notice that this was missing. It's the harmonic missing 1/2, right? And if we missing 1/2, what is infinity minus 1/2? It's still infinity, right? So that's not going to affect it at all. Again, this just goes to show you that when we see that addition that's going on between the fractions, it's just evidence of the harmonic series.